Okay, this is a pre-lab discussion to get you started to think about Lab 4, which is actually a two-part lab, A and B, that's going to take place in the third week of the class, titled How Much is Too Much Gatorade? So what you're building towards in this class is really the capacity to answer this question experimentally. So what you're going to do is in a group of 3, you are going to think about how much red Gatorade can a person drink in a day before consuming levels of red dye colorant that are considered potentially toxic. You're going to do this in groups of 3 or teams of 3, and you're going to preserve that same team over both parts A and B in the week that we do this work. So here's an example of the Fruit Punch Red Gatorade, which contains this red dye known as Red 40 or Allura Red. Turns out there is quite a bit of tension in the medical community about whether or not this has adverse health effects, especially in developing or younger children. In the United States, we don't have any regulation, but in the EU, it's banned in many countries. And for those that it's not banned explicitly, any product that would require its consumption requires that it contains some sort of warning label about its presence. And so generally in the United States there's an acceptable daily intake for this molecule, or ADI, that says you can consume 7 milligrams of this dye per kilogram of your own body mass for each day. So that's really the general criterion which will help you answer this question. But really then you need to think about, well, how much is in this bottle so that you can start to think about that, and how would you go about measuring this? Before I go into any more details about that, I'll just give you sort of an overview of the timeline. So on Monday morning at 9:30, we're going to have the actual pre-lab discussion. This is the pre-lab discussion. And that will serve to answer any last-minute questions. But actually before Monday, it's imperative that you meet with your group of 3. That group is posted on Canvas to complete the pre-lab. And the pre-lab are a series of guiding questions that help you think about designing an experimental protocol. And ultimately what you should bring to class on Monday morning is that experimental protocol. You won't have time that morning or that afternoon before lab to actually put it together. So it's important that you meet between now and then to go through these conversations with your. So then on Monday morning we'll talk for 15 or 20 minutes, answer any last minute questions that you have about your protocol design. And let me mention that the whole point of this is to model the true spirit of scientific research, which is often ending in failure. You're going to, based on what you know so far in this class, put together your best guess for how to measure this using some logic and some deduction. And then you'll get an attempt on Monday afternoon at 1:15 to execute that protocol, make some measurements, and see how close you get to what your expectations are, see what goes right, see what goes wrong. You'll then upload that protocol and your results to a shared spreadsheet, which I've linked in the other documents. And then on Tuesday, midnight, you'll have your post-lab questions due. They're sparser than they normally are, but the idea is that you're going to reflect on what you did as a group and the data that you collected in the context of the class data. What did everybody try to do? Because people will take very different approaches. And then on Wednesday at 9:30, I'll come back into the classroom. We'll have another in-class discussion, really reflect on what worked and what didn't collectively, and then you'll have an opportunity before Thursday with your group to then modify your protocol so you can make a second and final attempt. It's important to know that you will not be graded, especially on the first part, for your correctness. You'll be graded based on your logic, your deduction, your engagement, and your execution of the experiment based on what you know. But it doesn't matter if you get the right answer. But then you'll have a second attempt at this after a series of reflections throughout the week, which is really what we do as scientists. We try based on a hypothesis. It often fails, and then we reflect on it and we see what to improve, and then we do it again. And sometimes that process may take 10 or 12 or 50 or 100 times before we get the answer that we're satisfied with. And then Sunday, next Sunday, right before the 4th week, you'll have your Lab 4B post-lab due so that you are done with all your lab requirements before the final exam. So that's the schedule. So what will you have access to for these series of labs? Well, you'll have all the equipment in your lab drawers, and I've linked a list for you, and there's definitions for most of this equipment if you can't remember what all of those things do, so that you can design a pretty detailed protocol knowing what you have access to in terms of glassware and other equipment. You'll have access to the same Spec 21 spectrophotometer that you used in Lab 3. There's a link here to a video that walks you through its use again if you don't remember. You'll have the same cuvettes. Those are the glass test tube looking devices that contain the sample. If you choose to use the spectrophotometer, you will have access to fruit punch or red Gatorade for your tests, and then each group of 3 will get roughly 0.2 grams of pure red 40 dye in a vial, but you only get 1. So you're going to want to think about how to use that wisely as you do any math or calculations. If you try to make solutions of this red 40 dye, you will want to make sure that you don't exceed 0.2 grams of use. You'll get a new vial for each part because you're going to do this twice, right? You'll do your initial, see what you get, and then you'll get a second opportunity. So you'll get 0.2 grams for each trial that you do this experiment. First thing you should do as a group is read through the typical lab context that I put together. So that gives you a summary. That just tells you the question that you're trying to answer, the things that you should be able to do after you do this lab. So these are the learning goals, general workflow, how you'll be assessed, and then the context, which is the most important part. So read this a couple times in detail because it walks you through the idea of how absorbance of light relates to concentration, which might be useful for you in this process. And I'll give you a couple other pointers, but make sure you start here and read through this document thoroughly as a group. Okay, so the real question here is then, how does concentration of a molecule that's dissolved in a solution like water relate to the amount of light that it actually absorbs when you measure it, right? You've measured absorbance using a spectrophotometer. How does that absorbance change? The document that I just showed you, you should read first because that provides you really important context for this lab, but I'll give you a little bit of a quick primer here. So the relationship between the measured absorbance, or A, or absorbance, that's the thing you measure on your spectrophotometer, and concentration, or C, is defined by this really simple expression. We call this the Beer-Lambert law, or Beer's law for short. And so absorbance is equal to epsilon, or E, times concentration times L. Concentration, of course, is just the moles per liter of the thing that you're measuring the absorbance of. L is the path length. This is the width or the diameter of the cuvette that the light is passing through. So that's literally the width of the solution that you are passing light through. Of course, as you increase the width of the thing, then your absorbance will increase linearly as well. The trickier one is this epsilon value, which we call molar absorptivity, and this is a constant unique to each molecule that specifies how much light is absorbed for that molecule itself. Okay, so once you have this relationship, how can it be useful to you in designing an experiment? Well, you know how to measure the absorbance of a solution. The concentration is maybe the thing that you're seeking to know, how many moles per liter of something are present. The path length is fixed. That's a known quantity that you can measure the width of your cuvette. Most of them are 1.0 centimeters for convenience. But that presents this tricky situation where the molar absorptivity is an unknown and the concentration is an unknown. So how can you proceed? So let's think about what we have, what we know, what we don't know, which is a lot of things. So what you're going to be provided is the pure solid dye that looks like this. This is the molecule, that's its molar mass. You'll only get roughly 0.2 grams in a little glass vial that you'll get to use, but nothing more than that. So if you spill it, you're out of luck. This is what you're going to get, and we know that the relationship between the amount of light something absorbs, its absorbance, that's something you measure on the spectrophotometer, is this really simple linear relationship where there's some constant, epsilon, which we don't know, concentration, which might be useful to determine, and then the path length or the width of the cuvette, which is essentially a constant that we can determine based on which cuvette we use, often 1 centimeter. We also have this bottle, which has some unknown amount of dye dissolved in it, and we're again trying to answer the question, how much of this stuff can we drink in a day before it becomes toxic? And we're given a metric of toxicity that I mentioned at the beginning of this video and in the context document that I shared previously. So based on this relationship, Beer's law, if we were to take different concentrations of the red 40 dye that we might prepare on our own as solutions with known concentrations and measure the absorbance, they may look like this, where we have 3 different concentrations: low, 10 micromolar, 30 micromolar, and 100 micromolar at the highest, noted by the hue or the intensity of the red here. And what you should see here is the path length is constant and epsilon is constant, even though we don't know it. So in that case, absorbance is directly and linearly related to concentration. So as this went up by a factor of 3, then the absorbance also increased by a factor of 3. As the concentration increased by a factor of 10, we would expect an increase in absorbance at a factor of 10. So how is this useful? Well, remember, you still don't know epsilon, and you don't know the concentration in the Gatorade itself. This is the unknown. So in this case, you're using known concentrations and its relationship to absorbance to potentially think about what is unknown. So since you have the pure dye in solid form, you could potentially prepare standard or known solutions where you know the concentration because you calculated it, you weighed it on a balance, and you measured it in a piece of volumetric glassware. You could make as many of those as you want or need at whatever concentrations are relevant to you, which are all going to be important things to consider as you design your protocol. And if you know that concentration, then you can measure their corresponding absorbance. That would give you a table of values of concentration and known and measured absorbance. So absorbance and concentration. What can you do then? Well, you can make a plot where you have absorbance versus concentration and plot that XY data. So that might look like this, where we had our 4 original solutions. You may have more than that or less than that. That's going to be up to you to think about and use logic to deduce, and at the specific concentrations that you prepared them, so that you now have these data points of absorbance and concentration, which we know then how in Excel to make that plot and to then fit a trend line to this plot, which should be a straight line because we know that absorbance and concentration are linearly related. That's what this algebra means. So if we think about this in terms of y equals mx plus b, which you know as the equation of a line, how does Beer's law relate to this generic expression of a line since we have this line here? Well, we just plotted absorbance as the y, concentration as the x parameter. We do not have an intercept in this equation, so that means this goes away. And now, what does the slope of this line give us? So the slope is a pretty useful quantity if we think about what's left in this expression. Okay, so the last thing here then to consider is you have an unknown amount of red dye in your Gatorade. That's potentially the thing you want to measure. And so ideally, you then measure the absorbance of your Gatorade. So the absorbance of the Gatorade, that's something you can measure, but you don't know the concentration. Well, that's okay as long as you've done all this legwork, because as long as that absorbance lands between the low and the high concentrations of your line, then the equation of that line can allow you to deduce the ultimate concentration. That's the goal. So considerations that are important. Of course, what concentrations are you making these standards at? How many are you measuring? Are you measuring them each once or more than once? Are you measuring the Gatorade once or more than once? These are all important. One part of the pre-lab that will get you thinking is, over what range is Beer's law actually true? Is this infinitely true? As we keep increasing the concentration more and more and more, the absorbance just increases linearly? Or is there a practical limit with how much light something can absorb if it gets too dark, right? As the concentration gets higher and higher, the object gets darker and darker and darker and darker, then what happens? And so what we're really asking then is, what's a useful high point up here? What's the maximum reasonable absorbance that one can measure where this process is still sound? So you'll want to think about that, because that will then govern how you create these standards, and it may govern how you treat your Gatorade sample. If, for example, it's really highly concentrated in your Gatorade sample and ends up way up here, then perhaps you might need to treat your sample in some way to decrease its concentration. So those are all the hints that I'll give you to start thinking about your protocol. Remember, you don't have all the information. You may need to look things up. You may need to brainstorm. This is meant to be a real experiment. And so it should be tricky, it should be challenging, you should really rely on the collective wisdom of the group and not be afraid to make mistakes, because that's what science is. You're going to do this and give your best shot. You're not going to be evaluated based on correctness, but then you're going to get an opportunity to reflect on this and really think about what you do different and then do it different. And hopefully you get some improvement on the second time around.